Now what we saw was conservation of mechanical energy, right? Now, since we are talking about potential energy in all these videos, we'll see one more thing, that is potential energy which is stored in a spring, a compressed spring. See, that has tremendous amount of potential energy. Like when you compress a spring, you guys know that, right? How far the object will go if you just release it. Now, practically if you see, earthquakes are just like this, because see, the tectonic movements of the plates inside the earth, that's basically like a spring. It's a compressed spring. Like the two plates inside the earth will move, and that energy will be concentrated. Okay, and then it's like a compressed spring. So once that comes off, you feel that earthquake and movement of plates and all those things. So basically, compressed spring has tremendous amount of energy. Now that energy is potential energy. Okay, what you will be doing is how much of energy is stored in a compressed spring. That's what you're going to learn. Okay, now this is a very interesting concept because we use springs in almost every day. Like it could be shock absorber in your vehicle, or it could be anything. Okay, so how much of energy is compressed in a spring? Now for this, you need to know one basic thing. Here, the expansion or compression of the spring depends on how much of force you give, correct? Like more weight you hang across a spring, the more extension will happen, right? So how much of force are you adding to that particular spring? That's nothing but F. So F is proportional to X, X being the displacement in the spring, correct? Now to remove the proportionality, we introduce a constant. So we have F is equal to minus K into X. Now why do we get the negative symbol? That's a very important thing. Now if you look at the figure here, see, at position X is equal to 0, F is equal to 0, correct? Now if you look at the second figure, now as X is increasing, that means if X is more, then what is happening? F also changes, correct? Now if X is in the positive direction, then F will be in the negative direction. Whereas if X becomes negative, then F becomes positive. Because once you're moving it down or you're compressing the spring, correct? So in either ways, F, since force is a vector, obviously direction comes into play. So F and X, they move in opposite directions. This is the reason we get minus K into X. Okay? Okay, so we have the force, right? F is equal to minus K into X. Now this is what we call as Hooke's law. Okay, so this is based on scientists who have discovered this. Okay, now let's start about the work done. So work done was what? W is equal to integral of F into dx from x1 to x2, correct? Substitute the value. So we have W is equal to minus kx integral from x1 to x2, right? Now negative k is a constant, you can take it outside the integral sign. So this is one of the properties of integral, so which you guys will learn in the next year. So we have W is equal to minus k integral of x dx from x1 to x2. Now if you integrate x, you are going to get x square by 2. So we get W is equal to minus k into x square by 2. Now we have to put the limits from x1 to x2. Okay. Now since x1 to x2 we are doing, see, one important thing which you guys have to notice. Now we start from a position 0 and then we move on to a position of x, correct? So in this case, x1 is nothing but 0 and x2 is nothing but x, correct? So in place of the limits, you can substitute from x to 0 in place of x2 to x1. So we get minus half into k into x square minus 0 square, which is the same as minus half kx square. So here, whatever the work you're doing gets stored as potential energy in the spring. Okay, so we just figured out the potential energy which is there in the compressed spring, which is minus half kx square. Okay, why the negative half comes? Because you are working and that work is being stored as the potential energy, correct? So once you release the spring, that energy comes as kinetic energy or any other form of energy. Like the example of tectonic plate, it comes out as different energy. That's all. Okay. Now we did the whole derivation using integral sign, correct? Now we can also use straight lines and figure out what is the potential energy. Now for that, see, you have the xy axis, and then since the force value is given to be negative k into x, you get a straight line like this. Okay, so this is a straight line passing through origin. Now this has a slope of minus 1 by k. Okay, now what we have is, see, at this point we complete it to be a triangle. It's a right angle triangle. Now this distance is x, this distance is negative kx because it's coming down, right? Now what is the area of the triangle? Half base into height. So we have half x into minus kx. So you get it as minus half kx square. So the potential energy of a compressed spring is negative half into kx square. Okay, so understood what is the potential energy of a compressed spring. Okay, in the next video you guys will see certain problems based on this formula.